So this video is meant to show you just the basic functionality of the architecture for AGI I've been working on for 5 years. So the image here is just to illustrate it basically, and I'll walk you through it. It's not the full architecture here, of course, it's just the basic design. And so now you can see here the basic design is the brain is AGI is just all in one hierarchy, a collection of hierarchies really, and it doesn't make sense for me to have AGI any other way than to have it all work in a single collection of hierarchies. It would be like this for text, say if we only had text. So the brain is made up by little hierarchies, and little features build up higher features, and those features build up higher. They reuse each other, they're shared. And so if you hear 1,000 sentences in your life with the word animal in it, animal gets reused for all those sentences to build larger phrases, feature nodes. And so everything in your life will link to that node. Everything links to the same node, doesn't store it twice, the same node, animals, so only once it stores it. So the memories are all, it's a hierarchy of context, so it's all shared and you can jump around in it. So the basic design here is a hierarchy and everything works in it. So you've seen in the past the recurrent networks, the RNNs had looping in them, and then they got rid of it and they use a transformer. Today it's a feed-forward network. It doesn't loop around when it's recognizing something. So they got rid of that and they just use attention. But that's what I always thought in my architecture was there's not supposed to be looping, because the activation is just supposed to go up and recognize a word or phrase feature node at some certain layer and stop, because it's built of smaller parts reusing them. So the activation is supposed to go up and activate it and other similar ones. So it's just not supposed to be recurrent. There's no reason why it should be. So you can see on the internet now there's the Hutter Prize for 500 I think it's $500,000. So they have been trying to compress 100 megabytes of Wikipedia text, and the best record is 100 megabytes compressed to 14.8 megabytes. And I built a compressor. It's a predictor, a model of text that can compress 100 megabytes to 21.8 megabytes, and so it's pretty close to the 14.8. The Hutter Prize, a lot of people have been working on it really hard for like 15-20 years or something, and they're really smart people. They've been using all sorts of stuff like LSTMs and transformers and trying all sorts of stuff for like 20, 30, 40 years. So it's really hard, and they've been working on it. So my 21.8 is pretty close to the 14.8. It has some very fundamental things. I'm going to show you how it works in this. So like I said, I say it again, I don't understand how. I want to know how can I improve my architecture, because I only see AGI working in a hierarchy like this, made of little hierarchies, a collection of them, like this won't be here, and everything that the brain does is going to be working in the hierarchy, and I'll show you how. So with my algorithm I made, it's a compressor, lossless compression. It's just a predictor like this basically, and it uses a tree, and it's just predicting the next letter based on the context. So the way it works is I take the last 17 letters of the story as I'm walking through the file, in the text file. So I take the last 17 letters, I'm going to predict the next letter. So I take the last 17 letters. Now, before I save it into a tree, which doesn't reuse parts like this, it branches out and doesn't come back. So they don't really reuse each other, except for the very branch that you're on. So I take the last 17 letters. Before I save them in the tree, I search for 17, 16, 15, and then I'm taking all the observations of what comes next after that node in the tree. And then so I have 17 matches. Now, I might not get 17 matches. I might get, out of the 17 letters of context, I might only find like up to 7 letter long, and then 7, 6, 5 to the 1. And so in the hierarchy here, it would be finding matches of 6 letter, 5 letter, 4 letter, 3 letter, 2 letter, 1 letter. And then I'm seeing after those matches what comes next over here. And then the nodes also have counts on them, frequencies, so that how many times has it been accessed that you've seen dogs can jump? How many times has it been seen that the word R? How many times have you seen the letter J in the file so far? So every node has counts on them. So for the past context of the story, the last recent 17 letters in my algorithm, I'm finding the longest one first, which might be only 14 letters long, and then finding the next one, 13, 12. And the single letter doesn't look at the past context. It's just going to know what the next letter probability is on its own. Single letters. So then I'm going to, you have the predictions of what comes next. Like you'll have dogs can jump, then you might see a U, a T, an E, what comes next after that. So you'll see a node like dogs can jump up, and a dogs can jump far. So you're taking all the next letters and their counts. You have a set of predictions like A, 23 times seen come next, B, seen comes next 3 times, Z, seen comes next 1 time. And then you're going to take all 17 matches in the hierarchy and you're going to mix them, but you stop mixing like once you get enough counts in total. So if you're at the 17th letter, or say 14 was the longest you found, you see how many counts total come after that match, and then you're going to decide if you're going to keep going down, how much weight you still need. So it might be like 14, 13, and then you stop at 6 really, mostly. So, and then you're going to mix all those predictions together and you get the set of predictions what comes next, and you're going to see at the top the most likely next letter to come next. So basically the algorithm that I made is looking at the past 17 letters, and it's looking at various phrases and letters of the context that it's looking at. So like the last 13 letters, last 12 letters, last 8 letters, last 2 letters, and just even the letter probability of a single letter, what would come next. So it's looking at different views of that context, predicting what comes next. So far with my algorithm here, you have a hierarchy of parts with counts on them, like how many times you've seen it. And you're selecting multiple matches in it, seeing what comes next. You're looking at the total, how much weight, so you know, and then you're going to mix them. So like the matches in the hierarchy would all have common predictions, like jump, A, A, pip, A. So they all have the common same parent. So that's how it works in the hierarchy, is that they all send energy to the same one. So what my algorithm also does is it has a activation function where if the counts are too small, it doesn't really send too much energy up to the parent predictions. So, and so that's the basic idea of my algorithm, is that it's doing that, and that helps a lot. Now, the next thing to do in the brain here is you want to look at the past context and recognize similar words at the word level, aligned. So you want to basically window the last word and the last two words instead of really paying attention too much to like instead of ing down, you want to look at walking down. So you want to really look for matches in the hierarchy on word level instead. So anyhow, with these similar words, what happens in the brain is that if you store cats eat food, and then the next day you might hear dogs eat food. Dogs eat food. The moment it's accessed or stored, is going to be dogs finds out it's similar to cats because the context can eat is the same as the other one, right? Dogs can eat, cats can eat. So the leaking energy indirectly activates cats from dogs. And so now if you have a word, the words around it on both sides and the ones that are more closer do that. So you can find out, that cats and dogs are similar by probability percentage. And then that's the same as predicting next letter. You get the probabilities of what comes next. So you have the probabilities of translation here of what word is similar to another word. Now, you can also keep doing this recursively. Like you can find out that dogs is cats. Then you can say, I bought a cat. And then you can say, I love cats. So now I love becomes we bought, say, because of a word that, even though it's not same, you know that cat and dog is same. So, and then the third type, even more crazy, is you can have cats equal zebras, monkeys, bunnies, and then dogs equal zebras, monkeys, bunnies. And so you know that those two are same because they're both the same things. So the way this works is the word just goes up and activates similar nodes, a whole bunch of them. So in my algorithm, I didn't implement this yet, but it's the next stage. You want to have words in the last context. You're going to be matching similar phrases, and then they're all going to be giving you the predictions of what comes next with frequencies. And so you're going to have a lot of data, virtual data generated from it. So instead of adding more data to improve the accuracy of the frequencies, which works in the algorithm, if you give it more data, it gets more frequencies, it's more accurate at the prediction. You can also do the translation. You're activating similar phrases, and it's hence giving you more frequencies, more data, virtually for free in the same data set size. So now the next thing that I've been testing in GPT-2 is when a node is getting activated, it retains energy for a while, and so you can see in your text, your context, the most recent words will vote on the prediction words at word level that are more closer to the end of the context. So if you got I was walking down the street and seen some leaves is going to boost up the predictions like grass, tree, leaves. And especially if you've seen in the context, I was walking down the street and saw some leaves on the road, and that saw some, if you see later saw, it will predict some. So there's carriers in the context that even if you've never seen it in all of the data set, if you see it in the context, it will really heavily vote on a word. So so the brain is a hierarchy that's storing nodes with frequencies and retaining energy. And then the other thing you can see in Facebook's new chatbot Blender, you can see it uses a dialogue, which in my architecture I've known about for a few years now, is you basically hardwired nodes at the birth of the agent's mind. Like, the word food, you would hardwire it with reward on it so that it's usually always activated no matter what. So the dialogue is forcing it with a persona to always be talking about food. So the node is always activated. So unlike the energy that can fade away, the reward the reward on the node is always activated. So you never forget about food. And then you can say, if you told the password with the energy on it, you can forget about it. It remains in the brain, but the energy fades away. So you temporarily forget what the password is, even though you know it. And then the third type is that, you've seen it a few times, some word, and you forget it because it gets pruned away because it's a weak weight, doesn't have a lot of observations. So those types of forgetting are very important in the brain. There's like I said, the forgetting a node or not, and then there's energy you can temporarily forget or keep it in mind, on your mind, and then there's the reward that's always keeping it activated. So you can have reward on a node, and then so that's a lot of the hierarchy right there of the brain of my architecture. So it makes sense to me to have it all in the same hierarchy. Now, there's a lot I told you there about how the energy goes up. It's recognizing it. It will match a similar phrase. Recognize, translate, understand it. And then the prediction is part of that recognition. The recognition is going up, and then the prediction is what comes next. It's just the energy flowing up. So you have this brain here, you have the energy going up, and it's preferring higher layers if it has enough counts and ignoring the lower ones, as I told you with my algorithm that would be doing in here. So it already does that, but that's what it will look like in here, is it's preferring the higher layers if they have enough counts. And it has the activation functions, and it should leak energy to nodes that are similar, and then they're all weighing in on the same predictions, that they all have the same parents to the same nodes. Like, the phrase and the context will match. I was walking down the street, I was walking down the street, and she was running down the road, and they were traveling down the hallway, and so they all share it with frequencies, how many times comes. So it's giving you a lot of data. And then what happens is that basically it's all about the energy in the network. It's going up, preferring layers, they're all voting on, and then the energy retaining in it, and the reward dialogue. And so you have all this, and now another question is how do you get it there? They use back propagation in the modern networks a lot, to make the weights emerge. But in my design, you would just, well, at least if it was this simple in text, you would just add on new nodes on top, and you won't actually have to change anything, because a node is activated if all its children are activated. And so now you want to compress the network to prune away redundancy and weak weights. So if it has a few counts for too long, you can get rid of it. If you have dog and cat, you can merge the word into cogd instead of storing both cat and dog. It becomes a non-pure node. You can even do it for word level. You might have my dog and her cat. You can store her dog in one node and get rid of both those. Just store her dog. So it's a blend of both, but on the word level. So the words aren't mixed up, but the phrase, storing both the phrases in one phrase, her dog. So the there is a so you can there's a lot to the hierarchy. So when you are with the pure nodes, you have with the backprop, you won't need it for that because you're pruning. You just prune the weak ones, or you merge ones to get non-pure, right? So now with the other things here, you want to find out which ones do you want to merge. So there's probably a way to find that out in here, like with you prune the low count ones. So with the merging, you might look for ones that have low activity activation. So it's probably something simple. Now with the translation, the similar words activating similar nodes based on the context. Like I was sitting on the bank and the fish were bank is going to activate the TD bank. It's going to activate the beaver bank, and then other words are going to maybe activate this one more because the shared nearby context. So it's just a winning activation. But to do that, it would just leak. But if you want to not have to search for it, what happens is that when cat and dog do leak the energy, cat's going to activate dog from the shared context, then they wire together when they fire together, the saying. So when cat and dog do activate from all the energy searching and leaking, then they just strengthen a connection between each other, which is the same way as how it saves already in the hierarchy, higher layer nodes. Because when you're hearing something like can jump, it will activate this one, and make this node, and that's how that already works. So if you learn cat and dog are similar, it would just make a node cat dog, and so it'd be basically already linking them directly for you. Now I'm not sure how you'd exactly do you even need to do that in a hierarchy or just let it leak on its own? Not sure, but it does work in two ways like that. Now with the so the translation, so you have you're gonna have missing or rearranged words or letters, like typos and everything, and it will still activate at some certain amount, and it can be robust to that. And so you can see Word2Vector on the internet and GPT-2. They are using this sort of translation, and GPT-2, as I said, seems to use the energy. The words in the story are voting on the predictions. So so back to what I was saying, how do you do this? Well, you don't need back propagation to do that, because the similar words, you can find the top most likely probabilistically closest word to jump in the hierarchy by the energy. You don't really need to Now, with the activation function, how do you find that? Do you use backpropagation? In my design, to not use that and just do it the right way, you would have the, based on the counts, how many times it's been accessed, how many parent nodes it has, which is already part of my algorithm. It's looking at the total counts of all the parents. It's looking at how much to split energy too. So it's something probably there like that, how that's going to work when we finally get it figured out. And now, another thing you can do is you can first notice that when you hear stuff or repeat it back in the brain, like A, B, C, D, you can only go forward. You can't repeat the alphabet back unless you do a little trick in the brain that I won't get into. So there's order. If you gonna build a node from two words like can jump, if you hear jump can, it won't make this. It won't activate this node. It's gonna activate another node, jump can. So these nodes know which parent comes first. I mean, you can have multiple parents. I mean, you can have multiple children make up a node, like can jump fast around and they all point to this one, not just two. This hierarchy just happens to have two. I thought it was a good idea, but I guess you can have many. Instead of just having many parents, you can also have many children. So, anyway, now another trick you can do is you can, if you want to remember a node, like chair, you want it to fire on its own many times, boost it. If you're in the kitchen and you want to remember it, no matter what, you want to really boost it up. So you link it to a node that is really strong, like some word you love, like fries or something. The word fries might already be linked to a node called I want to remember something really bad. And then so you're linking the word chair to I want to remember this really bad. And then you can remember something in your brain by linking it, forcing it to some other node that's activated a lot. So now in the brain with the math, if you're going to do 2 plus 2, you know the answer because you've frequently seen it enough and it's really exact, and it's not just a similar okay prediction, it's really exact, right? So 2 plus 2 has to equal 4. When you see something big like 248 plus 321, the brain does not know the answer right away because it doesn't have it, so it has to do little simple matches. So like this one plus this one, this one plus this one, this one plus this one, then you get the full 3 digits, 824 from the two numbers that are each 3 long. So the brain is adding these two and these two and then these two, and then you get the three combined numbers. So the brain sort of has to hold on to some numbers, like in some node, while it's working with the other ones. So it is basically doing all that in the same hierarchy because the brain only stores one of each word only once, so everything links to it. Now, there's some redundancy. I mean, if you lose a word, if you lose a neuron in your brain, I mean, it's not lost. There's context that can repair it, but the brain probably might have like a cluster of nodes that stores the word can or something. So if you lose one neuron, it can still remember the word because there's others that store it. But I'm not sure about that, but somehow it's storing at one time but linking everything to it, or at least it seems that way a lot. Because you want it to link to everything, the same word. You don't want to store the same word again somewhere else. Now, so basically, I don't know what else to do with this. I mean, too much. I mean, there's a lot to it in my notes, but I'm just giving you the basic idea. So, like, this is my idea for AGI, to have a large hierarchy of lots of little, well, it won't be a total hierarchy here, just like cut in half here, a bunch of little hierarchies, and like little judges that all vote on the next prediction, or what you're translating, recognizing. So, this is the brain here, you have your hierarchy, and usually in a network, like I said, it does back propagation, and it is, can't really see the nodes, they're blended, they're not pure nodes, and but if we did it this way, you can pretty much see, you can see the nodes even if you blend them and they're not pure anymore, you can see it all. There's nothing that you can't understand about my algorithm I already made that compresses 100 megabytes to 21.8 megabytes. I fully understand my algorithm, and even if I also did the translating and the energy too, I can probably get, I don't know how far it will get down the compression, but pretty far, really far, probably, and I still can understand it all. So I'm pretty sure there's a way to make it definitely work in this. You can already, my algorithm, so I'm definitely sure, and looking for feedback what else to do with this, or why it's wrong. All I know is that there's a lot of different types of networks out there, like GANs and LSTMs and Transformer. They all seem to do the same thing, that they're compressing, making a model, and it is trying to predict the data on the evaluation, and it is learning a model, and it's compressing it, and it's a hierarchy of features, because you want them to be reused. So this is my hierarchy here. Everything works in it with the nodes, counts, energy, reward, and in my design too, my algorithm, it does online learning. As it predicts the next word, it pops out, stores it to the tree, and then it's predicting the next letter, it runs through the whole file. So it stores the letter, it pops out, does that both on decompression and compression. So in our brain here, if it had a goal to cure cancer, it would have a question pop into its mind always, like, I will cure cancer by trying to predict, it's going to peer into the word cancer, it's going to translate, see what comes next, look back in time, predict the future before it even predicts next letter. So basically it is answering its question and storing that in the brain, and then it is adding data. So it's learning its generations and evolving its thinking. It's the predictions in its mind are being added to the brain, and it's making up new goals. And the way that works is that it has, say you might want to become immortal, right? You're working on science, you're working on artificial organs, you have a reward for AI, and then your reward might, like, let's say you have a reward for food, you find out to get food you need to build artificial organs, right, to live longer. So the reward transfers to the node artificial organs, because they share the same context, and so the reward, because they're same, it leaks not only the energy but also the reward. And now this is always activated a lot. Artificial organs, you talk about all day, so you're going to ask new questions now. So the brain is evolving the data, evolving its goals, and it can always see what comes next. If it's a bad decision, backtrack and start back at the root. Now, the brain wants to use a lot of context to make a good decision prediction of what's translating or predicting what comes next. And truth is prediction based on the data, and trust is based on the context. Same with a friend hierarchy network. If there's a lot of aligned context goals, then you have more energy, works together in the brain, and they are aligned, so it's more powerful beam. The waves propagate. And so, anyway, I'm looking, how can I improve this? What is the actual way that other neural networks work? I mean, I understand it all here, I'm sure. I'm just trying to figure out what else is there to the brain. Because I have a working algorithm, I have a lot of theory that makes tons of sense, and I've tested other algorithms too, like GPT-2, and I don't see anything else other than this AGI working in a single collection of hierarchies. And all it's thinking, its evolving thoughts and goals work in the same hierarchy. So how can you add to this? Is it just the back propagation? Is it how we learn the activation function, how we update the counts? I mean, you just update them, of course, it's easy. And then how which ones to prune. What else can we do to it?